So we're going to have another look at how we might fit an interpolating polynomial to a set of data points. And we're going to just talk about a method here that we did in Eng 1060, known as the Lagrange interpolating polynomial. So Lagrange was a very famous mathematician from the 18th century, and he determined a very general formula for the interpolating polynomial. You hopefully will remember this. So, if we have a set of n data points, xi, yi, we can fit a degree n-1 polynomial to these data points, and we write it in the following fashion. Our interpolating polynomial y of x is equal to a sum of terms. The sum goes from I is equal to 1 to n. So if we have n data points, there's n terms in this expression. And there are two parts to each of those terms. First of all, there's Li of x. This is a function of x. The second term is the yi. These are the data values that we know. Okay, so the interpolating polynomial is written by a sum of these products. What are the Li equal to? Well, it turns out that the Li are also degree n-1 polynomials, and they're defined using this somewhat complex notation as in this equation here. So Li of x is equal to pi. Now pi is just equal to a product of terms. So pi j is equal to 1 to 3 of Lj is just equal to L1 times L2 times L3. Okay, so getting back up to Li of x, it's equal to a product of terms from j goes to 1 to n, except we don't let j equal I. That term is removed from this expression. And so what it is, it's a product of terms, x minus xj divided by xi minus xj. And so we actually write this out in a little bit more detail on the following page. Now, each one of these things here is called the ith Lagrange polynomial, and it's equal to the following. So, for the ith point, the polynomial is x minus x1 divided by xi minus x1 times x minus x2 divided by xi minus x2 times, and we keep going down until we get to the point xi minus 1. The point in here, which would normally be x minus xi minus xi, we don't include that because, well, it's going to give us some problems, right? But it turns out that that's not the only reason we don't include it, but we definitely don't include it. And then we do finish off with the rest of the terms. So there's n-1 terms in here, each with the power of x, so this then is an n-1th order polynomial. Where on earth does this formula come from? It doesn't seem very obvious, okay? So let's have a look at this and try and understand where this comes from. So, in order to help us understand what's going on, let's have a look at what the roots of this ith order Lagrange polynomial is. Okay, so what do we think the roots are? Well, the roots are whenever this is equal to 0, Li is equal to 0. Well, that happens when x is equal to x1, because if x is equal to x1, this term is 0. It happens when x is equal to x2, because that term is 0. X is equal to xi minus 1, xi plus 1, and xn. In fact, it's equal to 0 at every node point except x is equal to xi. We don't know what it is there, but we know it's not 0. So, the ith Lagrange polynomial, Li of x, is equal to 0 at every node point except x is equal to xi. Raises the obvious question, well, what is the value of the Lagrange polynomial at the point xi? Well, let's take our expression for the polynomial and let x equal to xi. This then equals, first term becomes xi minus x1 divided by xi minus x1. The second term is xi minus x2 divided by xi minus x2, etc., all the way down to the end. That's just equal to 1 times 1 times 1, which is equal to 1. So in summary, each Li is 1 at node point xi, and 0 at every other node point, xj. So we can write that in shorthand notation like this. Li of xj is equal to 0 if I is not equal to j, and it's equal to 1 if I is equal to j. Okay, so we're getting partway there to understanding why this thing might work. Let's have a look at what the fifth order Lagrange polynomial looked like for just some equispaced points. L1, L2, L3, etc. So they have all kinds of weird and wacky shapes, and we can see, for example, let's look at L3 in the top right here. We see it's 0. The first two node points, it's 1 at the node point 3, and that's 0 at the other node points. And likewise for the other polynomials. So the question arises then, well, if we multiply Li by Yi, what happens to the function value at all of the node points? So if, for example, we multiply L3 by Y3, let's imagine Y3 is equal to 1.5, just as an example. What we're going to do is we're going to scale the L3 polynomial. So instead of being 1 here, it's going to be 1.5. But it's still going to be 0 at all these other points because it doesn't matter what we scale it by. So the polynomial is going to look something like this. But it's still going to be 0 at all the node points. Likewise, the same thing will happen with the other polynomials if we multiply it by the y value that they're associated with. So, if we multiply L of x by yi, then Li of x times yi is a polynomial that passes through the node point xi, yi and is 0 at every other node value. We just saw that on the previous graph. So, we said the Lagrange polynomial is equal to this sum. Let's have a look at what the value of y of x1 is equal to. Well, it's equal to L1 of x1 times y1 plus L2 of x1 times y2 plus Lk of x1 of yk plus all the way down to the last term. L1 of x1 is equal to 1, and all of these red terms are 0. Therefore, y of x1 is equal to L1 of x1 times y1, which is equal to y1. We can do the same thing for the kth value. So what's the value of y of xk? Well, we just plug it into the Lagrange polynomial. Y of xk is L1 of xk times y1 plus all these terms here. This term here is equal to 1. All of the circle terms are 0. So y of xk is equal to yk. So, y of x is a polynomial that passes through all of the nodal points that we're given. And it must be the same interpolating polynomial as we would find using Newton's method. The main difference between the Lagrange method and Newton's methods is, in Newton's method, either the matrix version or the divided difference version, we're trying to find a set of coefficients that we can then use to calculate the function value anywhere. With the Lagrange method, we never find any coefficients. What we do is we say we can fit a polynomial using this pretty messy expression, actually, especially if n starts getting large, but we can computer code that easily. We never find coefficients, but we have to calculate the function value using this expression here every time we want to put a new value of x in. And so that can become quite expensive. So, both Newton's method and Lagrange's method, basically you're fitting a global polynomial. So if you have n data points, you're fitting an n minus 1th order polynomial. So it's a global polynomial that fits every data point. Global polynomials have potentially a lot of problems. Let's have a look at the graph on the right there. If we were to fit a 16th order polynomial to this data here, we're going to get something that looks like that. Now this function doesn't look like it's terribly badly behaved. There's sort of something maybe going on here that's not so good, but we're doing a pretty bad job here. But we would expect the data values across here, it looks pretty smooth, but we're getting enormous errors down here, down here, down here. So there's something gone wrong with this global polynomial. Let's have another look at another example. Let's look at the function y is equal to e to the negative 0.5x plus e to the negative 0.05x, and let's add some very, very tiny errors, 10 to the minus 5 magnitude errors to this, and then let's fit a 19th order polynomial to these 20 data points. Well, we can see we do actually a pretty good job most of the region, but as we get particularly close to the edges here and here, we start introducing really, really large errors. So, the bottom line here is high-order polynomials often oscillate wildly, especially if there's a little bit of error in the data. This is what we termed wiggles in Engineering 1060, but these are just oscillations associated with the fact that the interpolating polynomial, for a high-order polynomial, can introduce very large errors. If the data has a singularity, we also get large errors, and it turns out that in this particular case across here, on the right-hand side, the actual data look like this. So in other words, around about 1.5, there was a singularity in the data. And so the curve looked like this, and we were trying to fit a function where really we can't be fitting any kind of function in here. Okay. The other thing about fitting high-order polynomials is it's typically inefficient. Lagrange method in particular, enormous amounts of calculation. Newton's method, you have to invert potentially a large matrix, or even the divisor differences. There's quite a bit of work to be done. So it's inefficient. And finally, the problem with high-order polynomials is that there's no error estimate. We've got no idea whether we're doing a good job or a bad job. So we want to have a look at something else, perhaps, where we're not going to fit a global polynomial to all of our data.